Good day, grade 12 learners. Welcome to today's mathematics lesson. My name is Chapang Mapotsani. This lesson is brought to you by the Northern Cape Department of Education in collaboration with Pagama Research and Development. Now, grade 12s, in today's lesson, we are focusing our attention to probability, and this topic weighs around 15 marks of our paper 1. And remember, this is our last topic in our paper 1. And you must remember that this paper 1, or this topic of probability, it is divided into two sections. There's a section that focuses on grade 10 and 11 content on probability, and it's a section that is going to focus on counting principles, which is what we will deal with in grade 12. But for this lesson, we are looking at grade 11 revision part 1. Now, by the end of this lesson, grade 12s, this is what you should be able to do. We are going to revise grade 11 probability, and you must remember, this grade 11 probability also contains knowledge or contents from grade 10. So we are on this, in this revision, also revising grade 10 at the same time. In our revision, this is what we're going to focus on. We are going to identifying of independent and dependent events and product rule for independent events. So we are going to identify independent events. We are going to apply the product rule for independent events. We are going to work with Venn diagrams to solve probability problems, deriving and applying the formula for any three events A, B, and C in the sample space S. And this information comes from our CAPS document, and it is also coming from our grade 12 ATP 2025. Coming into this lesson, we must know the pre-knowledge from grade 10. So what did we learn about probability from grade 10? We have learned the use of probability models to compare the relative frequency of events with theoretical probability. We have used the Venn diagram to solve probability problems, deriving and applying the following for any two events in a sample space S. So we have worked with the Venn diagram that only contains the two events in our sample space. We have worked with the identity rule. You must know the addition rule for mutually exclusive events, and the rule is P is in brackets A and B is equals to 0 when we are saying the events are mutually exclusive. Then we are now saying P A or B is equals to A P probability of A plus the probability of B. And we are saying if A and B are complementary, then we are saying A and B are complementary if they are mutually exclusive. And we will go and dive deep into the concept of mutually exclusive when we are looking at events that cannot occur at the same time. And we are also going to look at a complementary rule. A complementary rule, we are talking about a complement of a particular event. To say, when I say I'm looking for a complement of A, we are saying we're looking at the probability of A not occurring. Right, now, outcomes. What are outcomes? So these are the important terminologies that we are going to use throughout our lesson, and we are going to use throughout our learning in terms of probability. Outcomes are different ways an experiment can turn out. So it is a result of an event. So when you're saying we are having outcomes, we are looking at the result of a certain event occurring. Sample space, it is a set of all possible outcomes of an experiment. So it is a set of all possible outcomes. For example, if I roll a die, how many possible outcomes can I get? I can roll a die, I can get a 1, I can get a 2, can I get a 3, 4, 5, and 6. So these are the possible outcomes from performing a certain event. If I perform an event of rolling a die, I have 6 possible outcomes that I can actually get. So in this case, even if I talk about maybe tossing a coin, so I can get a head or tail. How many possible outcomes do I have? 2, either a head or a tail. So that is what a sample space is going to do for us. It is going to give us what? It's going to give us a set of all possible outcomes. What is an event? An event, a subset of a sample space. So that's what an event is. It is consisting of outcomes that satisfy a particular condition. An event is denoted with a letter E, and the number of outcomes in the event is going to be NE. And what is probability? Probability is saying it is the likelihood of an event happening. The probability of an event is a ratio between the number of outcomes in an event set and the number of possible outcomes in the sample space. Now let's look at probability here. We are saying again, the probability of an event, it is defined as follows. Probability of an event equals to the number of outcomes in the event over the number of outcomes in the sample space. For example, I can just have a nice sample space here. Just gonna have 2, 3, 1, 5, 18. So if I want the probability of me choosing 1, for example, I'll just say it's 1 over 1, 2, 3, 4, 5 events in the sample space. Right. So we can say probability of E is equals to number of events, number of outcome in an event, which is NE, all over the number of outcomes in the sample space. So if I was looking for that of 2, so it's going to be 1 over, total is 1, 2, 3, 4 over 4. The total in the sample space was 4. Then where E is the event and S is the sample space, and the probability of an event, it is always a number between 0 and 1. So we are saying when you look at our scale, it starts from 0 is to 1. Can look at it in terms of decimals, in terms of percentage. So impossible to say there's a 0 chance or a 0% chance of an event occurring. Like unlikely, it is when we have 0.25, which is 25% of it happening. Equally likely, it's 50-50, so the probability is going to be 0.5, which is 1 over 2. Likely is 0.75, and we are certain that is going to occur, which is 100%. And the correct knowledge here, the language to use here, it is certain. Don't say always. So I think that is where we might miss it a bit. Then we are going to look at the Venn diagrams. The Venn diagrams, we are saying a Venn diagram is a visual representation of events in a sample space. And in a Venn diagram, we usually represent a sample space with a rectangle and the events with a circle. So the whole sample space, it is that rectangle there. Then an event, it is given in with a circle. And we are going to start by looking at inclusive events. What are inclusive events? Inclusive events, these are intersecting events. A and B are inclusive as they have elements in common. That means the probability of A and B occurring, we are going to calculate using the addition rule that says P is equal into A and B is equals to probability of A plus probability of B minus probability of A or probability of B. Remember, the addition rule is there, stipulated nicely there for us in our formula sheet. And we can now write it in symbols and say probability of A and B is equals to the probability of A plus probability of B minus probability of A union B. Right. So when we're saying we're looking at the intersecting events, these are events that have elements in common. So you can see event A and event B, and we can see event A are sharing the space in the middle there, which is A and B. That means if I have a 2, the 2 also exists for A and also exists for B. They are inclusive events as they have elements in common. So A and B are inclusive events as they have elements in common. So we are going to say the probability of A or B occurring, it is given from a formula sheet. It is P. Probability of A or B is equal to probability of A plus probability of B minus probability of A and B occurring at the same time. So the union of events, we are talking about the event that all occurs in both A and B in that case. So the probability of A or B, it is probability of taking out anything here or there. So it is a probability of getting a certain desired outcome in any of the events. Then we are going to say, remember our A and B are inclusive events if they have elements in common, and we are going to make a simple example here. The addition rule, we are saying probability of A or B is equal to probability of A plus probability of B minus A and B. Let's look at the events. So the events of A and B, where we are looking for events that are found in both A and B, it is 2 and 6. So there's a one in the intersection. So those are the ones in the intersection. Then the probability of A or B. What is the probability of A or B? These are probabilities that exist in both events. Right. So A or B, it is from A until B. So it's 1, 2, 3. So it's all of the events that are existing in my event, in both events. So it's 1, 2, 3, 4, 5, 6, 7, 8. So this is all of them, excluding the 9, because the 9, it is not part of event A or event B. Then we can now say number of events of A. How many are they? It's 1, 2, 3, 4, 5. So number of events of A, we're just counting how many events they exist in our event A. How do we do it again? We can separate the two events and say I have A, and in my A I have 1. I have 1. Okay, let me just make it bigger. Let's have it bigger. So in, for example, I have A here. I have 1. I have 4. I have 3. I have 6, I have 2. So even if I separate the event A, you can see there are 1, 2, 3, 4, 5, including those in an intersection. Then the event B alone, it is going to be 5, 7, 8, 6, and 2. So there are 1, 2, 3, 4, 5 again in B. So when we're looking at these inclusive events, we can actually separate the two events and look at them individually if you are having any challenges. Then we can say the number of events between A and B, it is 2 of them. It is the 6 and the 2, which is what we've also denoted there from the beginning. Then the number of events, which is A or B, which is for both of the events, which is this one. How many? 1, 2, 3, 4, 5, 6, 7, 8. So we're counting everything from 1, 2, 3, 4, 5, 6, 7, 8. All events that exist in both the events. Right. Now let's look at what you mean when we are looking at what we call mutually exclusive events. Mutually exclusive events are events that cannot occur at the same time. They are mutually exclusive. So exclusive, they are not occurring at the same time. So exclusive, the word there to exclude. So we're excluding here. A and B are mutually exclusive events as they have no elements in common. So there won't be any intersection because they have no elements that are in common. So we can see event A has its own elements, which is 1, 2, 3, 4, and event B, it has its own, which is 5 and 6 alone. Then we have 9, which belongs to neither. So when we have an event that is lying not inside, when you have an outcome that is not lying in any of the events, that outcome is going to be written just inside of the box, but not on the circles. So we can say, when these are mutually exclusive, we're saying the number of events between A or B is going to be the number of events of A and number of events in E. So it's going to be events in here and the events in them. So that is what we are getting there. Right. Then we are going to say the probability of A or B occurring, it is going to be the probability of event A plus the probability of event B. Then the number of events between A and B, the intersection, because this is in union there's no intersection, so it is 0. So the probability of A and B occurring at the same time, it will also be 0 because we don't have any events that they are sharing at the same time. Let's look at what is a complement. A complement of an event, it is an event consisting of all outcomes that are in the sample space, but they are not in that event, which is A. So when I'm saying I'm looking for a complement of A, I'm looking for any outcome but except the one that is in A, so but not in A. A and B are complementary if they are mutually exclusive. Interesting. So we are saying if two of events are complementary, they should be mutually exclusive, meaning we must never have events occurring at the same time, no intersection. Then we say the probability of event A plus the probability of event B occurring equals to 1. Then the complementary rule says P not probability of not A, which is a complement of A, is equals to 1 minus the probability of event A occurring. So the probability of A not occurring, it is 1 minus the probability of event A occurring in this case. Right. So the probability of not A, it is equals to 1 minus the probability of A. So we can see this is event A, then not A is going to be anything that is outside of A. Now, grade 12, let us look at the activity below. And for this activity, grade 12, you are going to be given 10 10 minutes to complete this activity, and your 10 minutes starts now. Welcome back, grade 12s. Let us look at our baseline activity. Number one, a sample space, it is made up of two complementary events S and T, where the probability of P with a prime, that to say this is a complement. Remember, the prime then refers to a complement, where P of S not occurring equals to 0.33. So we can say number A, complete the statement. The statement says PS plus PT, because both of them are complementary, so complementary events are equals to 1. So P and A equals to 1. Write down the value of probability of S. Interesting. What am I given here? I am given the probability of S occurring. So probability of not S, it is equals to 1 minus the probability of S occurring. Are we clear here? So what are we given? We are given probability of S not occurring, which is 0.33. So we are going to substitute 0.33 in our formula. We get 0.33 equals to 1 minus probability of S. We're just going to solve for the probability of S there. Then the probability of S is going to be 0.67. Write down the value of probability of T occurring. Okay, so probability of T occurring, remember we only have two events, so it is going to be the probability of not S occurring. In simple terms, to say if S is not occurring at 0.33, what's gonna occur at that point? We're going to have T occurring. I think that makes sense. Let me explain it again. If I'm saying the probability of S not occurring, I have only two events, S or T. So if S is not occurring at 0.33, then what's going to occur? Because something must occur. Then obviously T must occur. So that's what we're looking at when we are saying these are the complementary events. So in these simple terms, we're saying write down the value of probability of T occurring. Probability of T occurring, it is the probability of S not occurring, because they cannot occur at the same time. Or we can say probability of S plus probability of B is equals to T, it's equals to 1. Then probability of S occurring was 0.67. Then plus probability of T equals to 1. Then we see the probability of T, it is equals to 0.33. Let's look at number 2. Number 2, it says a survey was conducted among 180 residents of a small town to establish how many people contracted tuberculosis, TB, and or human immunodeficiency virus, which is HIV, during the last 5 years. The results were shown as follows. X people were diagnosed with TB, 30 people were diagnosed with both TB and HIV, and 69 people were HIV positive. 51 people did not have either of the diseases. Represent the information in the Venn diagram. Very important. When we are looking at the Venn diagram, we are always starting from the middle, we are going out. So that's what we are going to deal with. So we are going to start with 30, because 30 it is where both are TB and HIV. So we have TB, which is T, and H for the HIV. Right, now that's where we start, and we are going to subtract from them. Right, so always when you're dealing with probability, start from inside, we're going out, in, out. Right, from here I can look at the TB, which says X people are diagnosed with TB. So the total for TB, it is X. Are we clear? So that X includes the 30. But if I want the section of TB only, I'm going to say the X, which is the total. So for TB, I will say X, which is the total, minus the intersection, which is 30. So we start from the intersection, then when we get individual events, we're going to subtract. Then let's look at for HIV alone. The total people who got HIV are 69. And that 69, it represents what? The 69, let's go there. It represents everything in our event age. Because that 69 also includes the ones who have TB, because there are those who got TB and HIV. So 69 are HIV positive. Then how many are only HIV positive but doesn't have TB, or which is that space that I've highlighted there? Then we're going to look at our H, we are going to say is going to be 69, which is the whole of the h there, minus the intersection, which is 30. We get our value as 39. So 39 was the one for HIV only. Right, then X minus 30 is for TB only. Then they say 51 did not have any of the diseases, so 51 is going to be there outside of all of those events. Right, let's look at number 2. Now number 2, it says how many people contracted TB only. Okay, how many got TB only? To find TB only, we are looking for that section. And for us to find that section, what are we supposed to do? We are supposed to solve for that x because we have an x there. How do we solve for x? We add everything and we equate it to the total. So our total was 180. So I think this is 180. Was supposed to be represented on the previous question outside of the space to show that this is the total here. Then we're going to say x minus 30 plus the 30 plus 39 plus 51 is equals to 180. So this is a typo, so it cannot occur twice. 31, 39, this is the 39 there. It's equals to 180, which is the total. Then you're going to have x minus 30, so 30 and 30 will cancel out. Then I can see that 39 plus 51, I get 90. So an x plus 90 equals to 180, then x equals to 90. Remember, I'm looking for TB only, not x. Then I can now say TB only equals to this part alone, which is x minus 30, then 90 minus 30 equals to 60. So for TB only is going to be 60. And they just said how many people in this case. Let's look at number C. We have the 60 there, so I've replaced the 60 in. Calculate the probability that a random person selected or a person selected at random will only have been diagnosed with TB only. Probability of getting the TB only, which is the probability of T alone, we are looking at the probability of getting that part alone, excluding the intersection. So it's going to be 60 over the total is 180. Then we get probability is 1 over 3, which is 0.33. Then calculate the probability that a person selected at random will not have any of the two diseases. Probability of no disease, which is the one that is outside of the events, it is 51 over 180, which is 0.28. Now let us now zoom in our lesson. Here we are now looking at Venn diagrams, but we're looking at the 3 events. Venn diagrams, remember, it is a visual representation of events in a sample space, and we need to check that independent events are the 2 events that do not affect each other's outcome. So the events are independent, meaning choosing 2 colored marbles from a bag with replacement, thus the first choice doesn't affect the outcome of the second choice again. So what does it mean in this case? We have marbles. So we take the marbles out, and for the first event we take green, for example. Then when I go into my second event, I take the marbles, I put it back into the bag. So the total here, it is not changing. Total marbles not changing. And what are dependent events in this case? Dependent events are events where the first event A affects the outcome of the second event. What does it mean here? Right, it means now if choosing 2 coins from a wallet without replacing the first coin, the first choice affects the second choice, as the coin in hand is no longer available for the choice or second choice. Let's say I have two coins in this case, right? So I have 2 coins. I have R2 and R3. So that's the rand, R2 coin and 1 rand coin. Yeah, I think now let's work with the coins that were heavy. Yeah, there's no 1 rand, 3 rand coin. Right. So what am I having here? I have the 2 coins here. I take out R1. The probability of me getting 1 rand is 50%, right? Because there are 2 events here. So it's 1 over 2, right? So if I take this one, I don't replace it, then I can say that on the second event I'll only have R2 in the bag. So what happens here? It means now I have 100% chance of getting that R2. So you can see now, not replacing that coin of R1, it affects the second choice, because now this was 50%, now it is 100%. to get that. But then if it was independent, we're going to replace and we're going to remain at 50% again, right? So if you go back here on the independent events, I have R2 and R1. Then I take out R1, and the second event I replace the R1 again. So I can see we're still at 50% on the second chat. Right. Now let's look at the Venn diagrams. We're saying this is a simple visual representation of a sample space. Venn diagrams can be drawn based on the outcomes and numbers or probabilities. Hint, when using Venn diagram, you always start from the intersection and you work your way out. The Venn diagram we are going to focus on, we are going to look at 3 events occurring. Then we are going to see that we are going to start from the intersection where all 3 events are intersected. Remember, this is for the C, the event of C. Then if I look at more events here, this is the event for C. Then the events for B, it is also now intersecting at that center. Then the event again for A, they are all intersecting here, right? So that is the center for all of them and for those. So we can say now the shaded area represents A, B, and C, which is the intersection between all of them that we are looking at. Now, grade 12, let us now look at our example. Now for this example, let's look at it now. Let's zoom into this example. A school organized a camp for 103 grade 12 learners. The learners were asked to indicate their food preferences for the camp. They had to choose from chicken, vegetable, and fish. The following information was collected. Let's look at this one. We're looking at chicken, vegetable, and fish. So we have 3 at the same time. 2 learners do not eat chicken, fish, or vegetables. Okay, they don't eat any of this, so we know where we're going to plot this. 5 learners eat only vegetables, 2 learners only eat chicken, and 3 learners only eat fish. Okay, 21 learners do not eat fish. 66 learners eat chicken and fish. 75 learners eat vegetables and fish. And let the number of learners who eat chicken, fish, and vegetables be X. So that is for all 3. So why am I indicating this? Because that is my starting point. So I'm starting from where I'm having all 3 events occurring at the same time. So number 1, we are required to draw an appropriate Venn diagram to represent the information. Let's go here. So let's start. To get our Venn diagram, let's go through this one nicely. What am I going to start with? I'm going to start with the intersection, which I'm going to say start with X. So X is for all of them, right? And I'm going to look at where we are talking about only a particular event. 2 learners do not eat chicken, fish, or vegetables. These 2 learners do not eat any of the 3 because I have a chicken, veggies, and a fish. So these are the 2 learners. I have represented them there. Then we are saying 5 learners only eat vegetables. So we are going to start with the center. We go to the ones who are eating none of them. We are going to check the ones who are eating only that part. Then we are going to look at the 1, 2, 3 intersections. So these 3 intersections are going to be our last point. Now, 5 learners only eat vegetables. So 5 learners only eat vegetables, so they only eat vegetables. So that's why the 5 is there. It's only for the vegetables. 2 learners only eat chicken. 2 only eat chicken, and the 3 only eat fish. And our 3 in this case eat fish only. Right. And we are told that 21 learners do not eat fish. I am going to come back to this. It's very important there. So we are going to look at this one there, right? Or we can actually focus on this one right now and see what does it mean, right? It says 21 do not eat fish. So 21 do not eat fish, so they can eat both chicken and the veggies. So if they don't eat fish, it doesn't talk to the eggs there. So this is the point for 21, but that 21 will also include both the chicken and the veggies. Remember, this is the intersection. It's going to include both of them. So how do we work with that? We're going to have 21 because the 21 only works around chicken and the veggies, minus our 5 minus the 2. Right. So 21 minus the 5 minus the 2 and minus the 2 again in this case. So you can see that this is just 21 minus 7 and minus the other 2, which is the 1 which is outside there. Then we get our answer as what? As 12. So that is the value that we are going to get, because this is just 21 minus 9, which is 12. So you can see these are the ones that do not eat fish. They don't eat fish, and this one is also part of it there. 66 learners eat chicken and fish. So 66 eat chicken and fish, but we can see that this 66 is between the chicken and fish, and that will also include my eggs there. So to get the part of 66 that only eats both of them without the veggies, I'm going to say 66 minus x. Then I'm going to now look at the 75 learners that eat vegetables and fish. So 75 is vegetable and fish, which is for this intersection. Then we're going to subtract the what? The x in that case. So that is our Venn diagram there. Now let's proceed. Second question says calculate x. How many learners did you have? It was 103. So total value was 103. So I'm going to add everything here to get x. So it's going to say 12 plus 2 plus 2 plus 2 plus 12 plus 5 plus 3 plus 66 minus x plus 75 minus x plus x. In this case, it is going to be what? It's going to be 103. Then I'm going to solve for x here. Then my x, I just collect my like terms. I can see that the x and this x are going to subtract that. I remember 165 minus x. Then I get my x is equals to 62. So to get x all the time, we can add everything, including the ones that are not in the sample in our events. So everything in the sample space. Then we're going to equate it to the total for the sample space. Then we're looking at number 3. So the number 3 says calculate the probability that a learner at random eats only chicken and fish, no vegetable. Which learner is this one? Only eats chicken and fish. Remember we had x already. We just work around this part. Let's just go back a bit. We'll come back here. Right, we remember our x was 62, so we're going to say 66 minus 62. Then our x was 4 in this part. Then what is x here? The x here, it was 75 minus 62 in this case, and we are going to see this is going to be a nice 7 or 13. Apologies, 13 there. Right, so let's proceed here. So that's how we got this one. Remember, this was 75 minus 66. Oh yes, it is that 13 there. Then the x is going to be that 62 in the middle. Right, let us move on now. So we are going to say calculate the probability that a learner chosen at random only eats chicken and fish. Only chicken and fish, no vegetables. So only chicken and fish, it is only this part. So this includes vegetables, this intersection, although it goes with it, but it has veggies. Then this is the part we're looking for. So it's 4 over, the total is 103, which is going to be 0.04. Let's move on. Calculate number B, the probability that a learner at random eats only 2 of the given food. The choices can be chicken, vegetables, and the fish. So it's only 2 of the given food. So we are going to look at the probability of what? Of this. This is for 2. This is for 2. And that is for 2. So we're going to say 4 over 103 plus 13 over 103, which is the total, plus 12 over 103. So it is any 2. So any 2, it is the intersection for 2. This is for 3, and this is for the single and the single. Then the probability is going to be 29 over 103, which is 0.28. Now grade 12, we have activity 1 here. And for this activity, grade 12, you are given 10 minutes to complete this activity. And your 10 minutes starts now. Welcome back, grade 12. Let us now look at activity number 1. Let's go to number 1 in this case. Okay, let's start with the statement. A survey was done amongst 80 learners on their favorite sport. The results are shown below. 52 learners like rugby R, 42 like volleyball V, and 5 learners like chess, which is chess only. Then we're saying 14 learners like rugby and volleyball but not chess, 12 learners like rugby and chess but not volleyball, 15 learners like volleyball, chess and chess not rugby. Then X like all 3 types of the sport, and 3 learners do not like any of the sports. So we are going to start with X then. Right, to populate our Venn diagram, we're going to start with all 3. That's where we start all the time. So all 3, we're going to plot in X. We can even plot in the 3 because the 3 is any of the sports. Let's start here. So X is going to go into the middle. So that's what we're going to start with in this case. Then 3 learners do not like any of the sports. So those are the 3 learners there. After we've done or we've dealt with those, what are we going to do? We are going to look at the intersections. We start with the middle intersection, we go to the other intersection, then we can go to the individual events. Then we're going to go to this part. So remember, we are going to come back to this one. So 14 learners like rugby. The reason I'm going to come back to this is because these are the totals for each event. We're going to come back and explain that in detail. 14 learners like rugby and volleyball but not chess. So the 14 learners in this case, they only like rugby and the volleyball. So it's R and a V where they see them. So they like rugby and a volleyball but not chess. So it's 14 already. This is clear to say 14 only like both of them but it doesn't like chess, so the X is not included them. 12 learners like rugby and chess but not volleyball. So rugby and chess but not volleyball, so the X is not included, so the 12 already falls in there. Then we said 15 learners like volleyball and chess but not rugby. So already the 15 learners only like the 2. The X is not included again. After we are done with this now, let's now go back to the first part. There we are going out. So you see in, out. So let's now go outside. So they say 52 learners like rugby. Right. So from our learners, we are saying 52 of them like rugby. So what am I going to say? I'm going to say 52 minus, so the R, all of this R, that's what the R, the rugby speaks to. So what are we going to say here? Is 56. It's 52 minus the 12 minus the 14 minus the X. Right, so we are going to get is the following: 52 minus 14 minus X. We are going to get 26 minus X, which is the value that we are going to place in right there. Then we are coming this side. We are told that 42 learners like volleyball. So the total for the volleyball, all of this side, can see the total for volleyball, it is how much? It is 42. So we are going to say 42 minus 15 minus 14, right? So we're going to get the answer is minus X, because the X also is there, part of the V there. So you can see it's everything that I can shade nicely there, right? Then it's going to be minus X. Then we're going to get for volleyball, we're going to get 13 minus X. So that's what we get for the volleyball only, 13 minus X, right? Let's now proceed. We're going to say 5 learners like chess only. Oh, already this one they told us they like chess only. We should have started with this one. So this one is only chess. We can see the difference here. This one just said 52 learners like rugby. They didn't say rugby only or what. So the only there is a key part of the statement. So this one of saying chess only, it means it excludes all other stuff, all other sports, but it only remains with chess. So that word only is very important here. So that's what we are also focusing on. To say now here, it just says for 2 learners like volleyball. They didn't say only. So everything on the volleyball, it was 42. Then chess only is going to be 5 in that case. Let's move on. Show that X is equals to 8. How do we get X to be 8? Remember, to find X, we add everything in our events. So I'm going to say 26 minus X plus 14 plus X plus 12 plus 5 plus 15 plus 13 minus x plus 3. Don't forget this 3. Don't forget this 3 because we are also adding it when we are looking for the x. Then the all equals to the total. So our total was 80. Then we're going to solve for x. We get our x as 8. So we have shown that x is equals to 8. Right. After our x is equals to 8, let's just go back there. We are going to just place 28 minus 8, 13 minus 8. Whenever there's x, now I place in 8. So we're going to see that we get 26 minus x. We get how much? We get 18. Then 5 minus 13 minus x, we get 5. Minus 8, we get 5. Then x is equals to 8 in that case. So this is our nice completed Venn diagram. So after we get x, you need to do what? You need to come back and do what? And you need to come back and substitute x in our Venn diagram to get a completed Venn diagram. How many learners like rugby only? So this is not probability of rugby, it's N of rugby. So only rugby, it's 18. So only means that part alone. Right, now grade 12, let us look at number 4. Number 4, it reads as follows. Calculate the probability that a learner chosen at random likes at least 2 sports. Now let's check. Likes at least 2 sports. So it means at least 2 sports, it means from 2 and above. So it's going to be this one, this, that, and that. So it is all of the intersections called at least 2 spots. So we are saying the minimum is 2 and above. So this one is 1, 1, 1, and this one is none. So we're going to say this is going to be at least 2 types of sport is going to be 12 plus 14 plus 15 plus 8 all over 18. Right. Then this is going to be 49 over 18. Right. Now let us look at example number 2, grade 12. Example number 2, we are given that probability of A is equal to 0.4, probability of B it is 0.5, and probability of A and B is 0.14. Determine the probability of A or B. Let's populate this in our Venn diagram. The probability of A and B it is 0.14. Right. Probability of A only. So that means the total for A, it was how much? It was 0.4. So we're going to take 0.4 and minus the intersection, which is how much? Which is 0.14. So this one, to get this 0.26, we said 0.4 minus intersection, which is 0.14. Then we get the value there as 0.26. Then for this one again, we said 0.5, because the 0.5 is for the total, subtracting what? 0.14, which is our intersection here. To get the one for only B, we are going to get 0.21 in that case. Then to get this one, we know that it is going to be 1 minus everything we add here. So we just add everything together. Just say 1 minus 0.26 minus, or I can just say plus 0.14 plus 0.21. Then that is going to give me 0.39 in this case, which is our none of the events. Right, let's move on. Now to move on, let's look at number 1. So we are going to now say determine the probability of A or B. Probability of A or B, we are going to use the addition rule to say probability of A or B is equal to probability of event A plus probability of event B minus probability of A and B. The probability of A alone, or of A, it is 0.4. Probability of B, it is 0.4. It is 0.5 minus the probability of A and B, which is 0.14. Then the probability of A or B is going to be 0.61 in this case. Let's move on. Determine the probability of A, of not A, of a complement of an A. So the probability of not A, it is equal to the 1 minus the probability of event A. Then this is going to be 1 minus probability of event A. Remember, total of A, which is the whole circle there, was 0.4. So 1 minus 0.4. Then the probability of not A equal to 0.60. Or what you could have said, probability of not A, we just add the events that do not include A, which is 0.39 plus 0.21. then we get 0.60 as our probability of node A. Let's move on. Now, the question number 2 says, are events A and B mutually exclusive? Give a reason for your answer. Remember, mutually exclusive, it means no intersection, no events in common. And if you can see, we have events in common here, there's an intersection here. So the answer is no, because probability of A and B occurring at the same time is not equal to 0. There is a probability of A and B occurring. So what we are dealing with in this example, we are looking at a type of example whereby our events now, they are probabilities. The first example we dealt with, it was events whereby it was actual number of events. Here we are dealing with an event, our sample space that has probabilities as given. So that's why I said 1 minus to get the whole for the total sample space. Now, number 3. There is number 3 says, are events A and B independent? Give a reason for your answer. We can now see that probability of event A and B, it is 0.14, and we need to check the independent events to say, now the probability of A multiplied by probability of B, what do I get? They are independent if the two are equal. So let's continue. Yes, they are independent, because to prove that events are independent, the probability of A multiplied by the probability of B, it must be equals to the probability of A and B. So that's how we choose, or we now decide if the events are independent. Now, grade 12 above, we have activity number 2. And for this activity, grade 12, you are given 10 minutes to complete this activity, and your 10 minutes starts now. Welcome back, grade 12s. Now let us look at activity number 2. We are given probability of A equals to 0.3, probability of B, it is 0.65, and probability of A or B is 0.74. Remember, these are 3 probabilities that are given to us, so we are supposed to represent these probabilities in a Venn diagram. So we are dealing with the Venn diagram that speaks to the probabilities now. Now, to deal with the probability of A and B, we are just going to apply the addition rule. Right, the addition rule is going to be as follows. We are going to say A or B is equals to probability of A or B is going to be 0.74, because we are applying our addition rule. It's equals to the probability of A, which is 0.30, plus probability of B as given is 0.65, minus probability of A and B, because this is what I'm looking for. Then the probability of A and B, it is now going to be 0.21. Let's proceed. They say now represent the above information in a Venn diagram. To represent in a Venn diagram, we know very well that the probability of A and B, we found it to be 0.21 in this case. Then we know that probability of A is 0.30, so we're going to say 0.30 minus the intersection, which is 0.21 in this case. Then we get our probability there as 0.09. Same thing that applies to B. We are now saying for B, we are going to say 0.65 subtract in this case 0.21 again. Then we get our value as 0.44. Right, then the probability of none of them, we're going to say is 1 minus, because these are probability events, so the total here must be 1. So these events are represented as probabilities, so the total events here must be 1. So for everything in the sample space must all sum up to 1, because probability maximum value is 1. So we are now going to say 1 minus 0.09 minus 0.21 minus 0.44. Then this is going to give us 0.26, which is what we're having of none of them. Or we can say it, the probability of none is equals to 1 minus 0.74, because 0.74, remember, it is for all of this. All of this is going to be 0.74. Then to get that one is going to be 0.26. Then the 0.26 It is for none of these events that we are working with. Now, let us now look at number 2. Are the events A and B mutually exclusive? No, because probability of A and B is not equal to 0, meaning we have an intersection here. We have the intersection, and probability of A and B occurring is 0.21. Are the events independent? Give a reason for your answer. Remember, for events to be independent, we are saying independent event is when A, probability of event A multiplied by the probability of event B is equals to the probability of event A and event B occurring at the same time. So probability of event A and B occurring, we already have it was 0.21. Then probability of event A multiplied by the probability of B. So this is going to be probability of A is 0.30 multiplied by the probability of B, which is 0.65. We get 0.195. So no, events are not independent. And what is the reason? Is because probability of A multiplied by probability of B is not equal to the probability of A and B occurring at the same time. Right, grade 12, this is our homework. And for this homework, grade 12, I'm giving you only 5 minutes to copy down the homework. Right, now let us look at our summary. For our lesson, we have focused on mutually exclusive events, and we are saying these are events that cannot occur at the same time, and we have dealt with the addition rule for mutually exclusive events where probability of A and B occurring, it is 0. And remember, under mutually exclusive events, when you look at the Venn diagram, we can see there won't be any intersection. Right, so we say the probability of A or B, it is equal to the probability of A plus the probability of B. Number 2, we are looking at, or we focused on the complementary events to say A and B are complementary if they are mutually exclusive, meaning if they cannot occur at the same time, if there is no intersection between A and event B. Then we're saying the mutually exclusive event, we're saying complementary rule is probability of A plus the probability of B is equals to 1. To say the complementary rule will say to us P not A, so the probability of A not occurring is equals to 1 minus the probability of A occurring. Then number 3, we have also populated our information on a Venn diagram to say a Venn diagram, it is a visual representation of events in a sample space. Then number 4, we have dealt with identifying of independent and dependent events, and to say to identify whether events are dependent or independent, we are saying the probability of A and B should be equal to the probability of A multiplied by the probability of B. If the two are not equal, so these are independent. If the events are dependent, that means the two are not going to be equal. Right, for our next lesson, we are still focusing on revision, grade 11 revision for probability, and we are going to look at the second part of our revision. And for this revision, we are saying we are going to use 3 diagrams. So we're going to look at the use of 3 diagrams for probability of consecutive or simultaneous events in which are not necessarily independent, and we are going to look at the two-way contingency tables for the probability of 2 or more events to determine whether or not events are independent. So next lesson, we are looking at the 3 diagram, and we are also going to look at the two-way contingency tables where we are going to focus on the dependent and the independent events. Thank you. Enjoy the rest of the day.